All right, today we're going to talk about how to use integrals for position, velocity, and acceleration in the context of particle motion. So remember back when we talked about particle motion, when we were talking about derivatives, we had a particle that was moving along the horizontal line, so like the x-axis, and we used s of t for position, or sometimes we used x of t because we're moving along the x-axis. Velocity is v of t, and then acceleration is, of course, a of t. So now that we've added integration to our toolbox, we can do more than we were originally doing with particle motion. So here's just a think about it example. Your teacher, that's me, moves along a straight line at the front of the classroom according to values in the table below. Now, we don't have carpet in squares, but we do have the ability to think about that. So let's pretend that this carpet has squares. So as time goes by, your teacher's position at the front of the classroom is measured in carpet squares. So let's see, how far is your teacher's ending position from their starting position from 0 to 4 seconds? So the starting position is at 2, so I'll make a number line to help you think about it. So if here's 0, starting position is at 2, ending to position is at 18. So how far did your teacher travel? 16 carpet squares. But what is the distance your teacher traveled from 0 to 4 seconds? So that means how far did your teacher go to the left and to the right in total? Even though they ended up 16 carpet squares to the right, let's take a look at how we started. So from here to here, starting at 2 and going to -2, we moved 4 carpet squares to the left. Then from here to here, we moved back 2 carpet squares back to 0. So 4 and then 2. And then, okay, this is clearly not a very scaled number line. And then from here to here, from 0 to 2, another 2 carpet squares, and then from 2 to 18, 16. So even though at the end of the story, you've only gone from 2 to 18, you have to include at the very beginning the fact that you bounced back to -2 and then back to 0. So in total, you end up going 4 plus 2 plus 2 plus 16, which is 24 carpet squares. So how could you write that in integral notation? We are finding the distance from 0 to 4 of x of t. But what we're going to do is we're going to take the absolute value of that. Because what that does is that includes distance that we go to the left, and it includes distance that we go to the right. So this is what that represents, and that's 24. So even though I only moved 16 carpet squares, don't forget the fact that I also did a little dance over here as well. So the displacement is 16, but the total movement is 24. So let's take a look at example 1. A particle moves along a horizontal line between 0 and 8. The velocity of the particle is given by that big old equation that I'm not going to read out loud. And the position is given by s of t. And it is known that s of 0 equals -3. So first, we want to find all the values on the interval for which the speed of the particle is 5. So remember, speed is the absolute value of velocity. Remember, speed is the absolute value of velocity. Velocity is how fast you're going plus direction, but speed doesn't care what direction you're going. You could be going 5 to the left or 5 to the right because you're moving along a horizontal line. So we want to know, when is the velocity? When is v of t equal to either 5, or when is it equal to -5? So the good news is this is calculator active, so we can head over to Desmos. And we can type in that crazy equation. So v of t equals t minus 3 times the natural log of t plus 2 plus 2t times the sine of t squared over 12. So there is that crazy equation here in Desmos, and we want to know when that equation has an output of either 5 or -5. So y equals 5 and y equals -5. And remember, we're looking between 0 and 8. So we're going to find the locations between 0 and 8 where this has an output. So right here. Oh, wait, I'm sorry. We're looking between 4 and 7, not 0 and 8. This problem says between 4 and 7. So this isn't between 4 and 7, but this is, and this is as well. So these locations, oh, wait, no, this is not. Woof, sorry, y'all. Okay, these are the two locations where there is an output of either 5 or -5, where we have a velocity that gives us a speed of 5. So those locations between 4 and 7 that have an output of either 5 or -5. So the inputs are t is either equal to 5.621 or t is equal to 6.520 seconds. So let's write an expression involving an integral that gives the position of s of t. Use this expression to find the position of the particle at time t equals 3. So what that means is this. When we've given v of t, if we want to find the acceleration, we take the derivative. But if we want to find the position, we integrate. So we're going to work backwards to get the position s of t. So the position s of t is going to equal our starting point, because it is known that we're starting at s of 0 equals -3. So our starting point is -3, plus the integral. And since this is from 0 to some time t of, v of x dx. What this does is this allows us to take this time and plug it in for our x value at any time that we want. So how do we evaluate this at t equals 3? We can just type this into our calculator exactly as is. So we already have v of x in there, which is really nice. Or we've got it in as v of t, but that's fine. So we are going to do -3 plus the integral from 0 to 3 of v of x dx. And that tells us the position of the particle after 3 seconds. So the position of the particle is -6.263. Okay, next we're going to find all the times t over the interval where the particle changes direction. Remember, the particle changes direction when the sign of v of t changes. So direction change happens when v of t changes signs. This occurs at, let's go to Desmos and find where that occurs. So this occurs at, and we're looking between 0 and 8. So this occurs right here and right here. So these are the two locations where the particle is going left, and then right here, it switches and goes to the right. It's going to the right, it's going to the right, it's going to the right, and then here it switches again and starts going to the left. So these are the two locations. At t equals 2.341 and t equals 6.127. Is the speed of the particle increasing or decreasing at t equals 7? So remember, for speed to increase, either velocity and acceleration must both be positive or both be negative. So they must be the same. So let's find v of 7 and let's find acceleration, which is the same thing as the derivative of the velocity. And if they're both the same sign, we'll know that there is speeding up happening. So let's see v of 7 and v prime of 7. So since those are both negative values, it means the particle is speeding up. So the particle is speeding up because v of 7 is negative and v prime of 7 is negative. All right. So this is just like the problems we did in the past with particle motion. The only difference is now we can't just take the derivative, or we can also take the integral. So we can work in both directions. If we're given the velocity, we can integrate for position and we can differentiate for acceleration. So here we've got an example of an amusement park ride called the Space Shop. So it gently raises riders up a tower and then bounces them up and down. So here's the velocity. So we can see the speed and direction. We can see when it's getting faster and slower, and we can see if it's moving up and down. So find the total distance the space shot travels from 0 to 14 seconds. So what that means is we want to think about all of these chunks both up and down and add them together. So another way to think about that is this is positive as far as distance goes. Even though it's down, it's still a distance. So we don't care if it's going up or down. We just want to measure the distance. So we're going to find the integral from 0 to 14 of the absolute value of the space shot of v of t dt. So use your counting skills to find the areas of these. If you want to pause the video and do that, here, this is 100, this is 60, this is 40, and this is 80. So all together, when you add up those four values, you get that the ride travels 280 feet in 14 seconds. So when does the space shot change direction? Remember, direction changes because here it's going up and then down and then up and then down. So it changes direction at these three locations. So the space shot changes direction at t equals 6, 8, and 10 seconds because v of t changes signs. At what times in the interval is the space shot the highest? How high is the ride at that time? So let's take a look at the possible locations when the ride is the highest. The ride is going to be at its highest after periods of going up. So here is a period of going up. And so one possibility for the ride being at the highest is right here at 6 seconds. Another place the ride has been going up is right here. So another possibility is that the ride could be at its maximum at 10 seconds. We don't know which one, so let's figure it out. We want to know the position. So if we're given velocity and we want to know what is the exact position of the ride, how high is it, we want to find s of t, we can use integration to get that done. So let's find how high up the ride is at 6 seconds by integrating the velocity to get its position. And let's also find how high up the ride is at 10 seconds by integrating the velocity to find its position. So from 0 to 6, it's gone 100 feet up in the air. So that's how high it is. Now from 0 to 10, it's gone 100 feet up in the air. Then it went down 60 feet, but then it went back up another 40 feet. So that is 80 feet. So the maximum height occurs at 6 seconds because that is when we are 100 feet in the air. So how high is the ride at that time? The ride has a max height of 100 feet at t equals 6 seconds. I was going to write the word 6 like a crazy person. Okay. Write the expression for the ride's acceleration, velocity, and distance from the ground that are valid from the time interval 10 to 12. So let's start with acceleration. Acceleration is the derivative of v of t. So acceleration, a of t, is the same thing as v prime of t. And that's the slope, right? So what is the slope between 10 and 12? If we go up here and we look between 10 and 12, that's this slope right here. And that is a slope of down 40 over 2. So negative 40 over 2 is the same thing as negative 20. So our slope is negative 20. Now let's find v of t. That's just our output on that graph. So our output from 10 to 12 let's write a function for this little bit. We know the slope of it. Let's write a function for it. You have some options. We know the slope is negative 20. We have that already. So you can use this point right here or this point right here. So you can use the point 10, 0, or you can use the point 12, negative 40. I'm going to use the point 10, 0 because I like working with zeros when I can. Zeros make me happy. So we're going to write y minus our output is 0 equals our slope negative 20 times x minus 10. And if you want to clean that up, you can. You can write that as v of t is equal to negative 20t plus 200. And then finally, our position is going to be the integral, which is the area underneath that section. So the area underneath that section is going to be from here to here, the integral of this little chunk right here. So how can we look at that? Well, first, we know that our position right now is 100 minus 60 plus 40. So right now we know we are 80 feet in the sky right here at 10 seconds. So we're 80 feet in the sky. That's our position. Remember, this is velocity, but 80 feet is our position. And then we want to add this integral. So 80 feet plus, starting at 10 seconds to any time t, we want to integrate the velocity function. And if we do that, we can write this as 80 plus 10 to t, and then we can plug in our function negative 20x plus 200. I'm running out of room. dx. So this is our 80 as our starting position, and then the area under that curve, anywhere from 10 to t, and t has to be between 10 and 12. All right. Let's do some multiple choice questions with particle motion. A particle moves in a straight line with a velocity of v of t meters per second, where t is time in seconds. At t equals 5, a particle's distance from the starting point is 6 meters. What is the total distance the particle travels between 5 and 10 seconds? So this does not care about the starting point because it just wants to know what happens between 5 and 10 seconds. So this is kind of a decoy information. We don't care that it's starting at 6 meters. We just want to know how far it traveled after that. So the answer is going to be C. Remember, we take absolute value because we don't care about the displacement. We care about how far it's moved to the right and to the left. So, what I mean by that is this. Well, first of all, let me not do that. Say that I was running around at the front of the classroom as I am wont to do. Okay, this is just going to be messed up, and that's okay. So here's the front of the classroom. Here's a Promethean board. Here's my little podium. There's me, my unruly hair. Okay, so let's say that you watched me go over here. I don't know how many feet that is, 6 feet. And then you watched me go back here 4 feet. And then you watched me go over here another 10 feet. The total distance that I traveled was 6 plus 4 plus 10. So you watched me travel 20 feet. But my displacement is how far am I now from where I originally started? So my displacement is just this value right here. So I traveled 20 feet, but my displacement is only 2 feet. So 20 feet total displacement. And you could even say -2 because I moved 2 feet to the left. Okay, so this next problem. A particle moves in a straight line with the velocity blah, blah, blah. At t equals 2, the particle's distance from the starting point is 10 meters. What is the particle's displacement? There we go. So we don't care how far it travels. We just care about how far it ended up from the beginning. So how far did it end up from the beginning? We're going to choose the one that doesn't have absolute value because as we move to the right, it will add, but as we move back to the left, it will subtract again. So this is going to be our answer. So this next problem just gives us a chance to interpret different situations. So particle is given its position by x of t, the velocity is v of t, and the acceleration is a and t. And you're going to fill in the table using a noun, unit, and time. Hey, that should look familiar. So let's do it. If you see an integral expression like this first one, what does that mean? That is where the particle is positioned. It's not its distance, it's not its displacement, it's just where is it in space. Position in space. Units. In this case, we were told feet. So that is going to be feet from origin. And time is at 4 seconds. So this next one, and I do encourage you to pause the video and try and fill this out before we go over it. So this next one, the change in position in particle, that change happens in feet. And when does this occur? From t equals 1 to t equals 4 seconds. All right, this next one, this should look familiar. That's the average right there. So that is the average speed of the particle. In feet per second from t equals 1 to t equals 4 seconds. This next one is the position of the particle, the position in space. Please let me point out to you that this is the same as the first row because x prime, the derivative of the position, is the same thing as velocity. And this is at t equals 2 seconds because that is our ending spot. So we know the position at that time, just like up here was t equals 4 seconds. This next one is the total distance the particle traveled. And we know that because of the absolute value. Otherwise, we'd just get how much it was displaced in feet from t equals 1 to t equals 4. And then finally, the average acceleration of the particle. We know that this is the average. So if speed is in feet per second, acceleration is going to be in feet per second squared. And the time is from t equals 1 to t equals 4 seconds. So this cheat sheet below is just to help you think about all of the different ways we can think about particle motion. Keep in mind, these are the important ones. Total distance is given with absolute value, but displacement is just how far did it travel or where did it land? After going left to right, where does it land relative to its starting position? So those are important ones to make sure you have under control.